Hi everyone, I appreciate all of you joining my presentation. I'm Yeongsik team, a postdoc at Rensselaer Polytechnic Institute. I'll be talking about the photopolymerization in this phase separation of polyethylene glycol, polypropylene glycol, and polytetrahydrofuran in photocurable monomers. These are the experimental details to see the photopips, which stands for the photopolymerization in this phase separation. I used a photoinitiator TPO and to calculate photocurable monomers and three different polyesters, PPG3400 and PPG4000 and polyTHF2900. The number marked after the polymer refers to the number of average molecular weight. For sample preparation, I mixed the two monomers in a 3:1 ratio by weight and added 0.5 weight% of TPO. So this is named the neat resin. Polymer was added 15% by weight ratio for the phase separation study. I've used our reactive UV transmittance measurement apparatus to see the in situ optical turbidity during photopolymerization. This is the simple scheme to understand what the UV transmittance is in my study. The UV light passed through the sample and we measured it. Here the transmittance is expressed as the ratio of UV intensity over time IT and UV intensity without resin, I blank. When you look at this UV transmittance curve as a function of time, you can see the polyester structure effect on photopips. Compared to resin showing a monotonous slight increase, the resin with 15% polyester added exhibit more dramatic change in UV transmittance due to phase separation during photopolymerization. The induction time as a marked triangle is similar for all three polyesters, but the UV transmittance curve of those three is very different. So PEG has only a small change, but PPG is showing a big change. The optical turbidity due to phase separation increased in the order of PEG and poly-THF and PPG. So looking at this UV transmittance curve of this three polymer resin as a UV intensity increase up to around 100 milliwatt per square centimeter, the induction time is decreasing. This is because the initiator can be activated by supplying a sufficient number of photons to the resin in a short time at high intensity. And the increase in optical turbidity according to the polyester type is evident not only with low intensity but also high intensity. The difference in optical turbidity depending on the type of polyester is due to the compatibility between polyester and photocurable resin. To compare the solubility parameter of the materials to check the compatibility between the polyester and the resin, the solubility parameter of the polymer increase in the other PPG, poly-TH, and PEG showing following in this table. The solubility parameter of resin can be estimated as around 25.9 as the monomer ratio and its solubility parameter. And we can see that the greater the difference in solubility parameter, the smaller the compatibility by following this simple equation. As a result, the least compatibility with photocurable resin is PPG among three polyesters. In the UV transmittance result shown above slide, the greatest increase in optical turbidity of PPG can be attributed to the least compatibility. In conclusion, we developed the UV transmittance apparatus with controlled uniform intensity, and it was applied for the study of photopips using polyesters. And PPG was the best choice as the phase separating polymer additive among polyesters for pronounced incompatibility with the photocurable resin for the accurate measurement of the induction time or critical energy on photopips. Thank you for joining my presentation. For more detail, please have a look at the uploaded PDF file or send an email to me. Thanks again.